Hey, Mr. Harridan here. We're going to go over calculating enthalpy changes of a phase change diagram. This goes back to chapter 3 here. This is the temperature over here, and this is the potential energy, or the time. Okay. You remember that there are 3 phases in a phase change diagram: solid, liquid, and gas. Right? Going from solid to liquid, that would be melting. Liquid to solid would be freezing. Liquid to gas would be vaporization. And gas to liquid would be condensation. Remember, there were 2 more phase changes. There was solid to gas, that's subliming or sublimation, and gas to solid was deposition. Remember, 3 of these are endo and 3 of these are exo. Remember that melting is endo, vaporization is endo, and sublimation is endo, because to melt something you have to heat it up on a stove. Freezing is exothermic, condensation is exothermic, and deposition is exothermic. That's our review of chapter 3 right there here. But we're going to use steps for solving for the diagonals in the graph here. The diagonals in the graph look like that. Those are the solid, liquid, and gas. We're going to use this equation here. Delta H equals mCp delta T. Delta H is the change in heat, which is called the enthalpy. Later in physics, you'll learn that work and enthalpy are pretty much the same thing or they're related. So, yeah. So you're going to have the mass in grams, the specific heat capacity, which is joules, grams, degrees Celsius, and the temperature change in degrees Celsius. Remember, temperature change is equal to T final minus T initial. Remember, it's always final minus initial when you're doing those kinds of equations here. Specific heat capacity is the amount of heat required to raise 1 gram of a substance 1 degree. Degree, Mr. Harridan, write the word degree. Celsius. It's a standard for a specific substance. Now, that's the solid, liquid, and gases. That's the phases. This is what we're going to do for the phase changes. I'm having pen issues. There we go. Phase changes. We're going to use this equation here. Delta H equals moles times the heat of fusion. This is for freezing and melting. This is going to be the flat part of the graph. Okay. Delta H of fusion is called the enthalpy. And I keep misspelling enthalpy, but that's okay. Enthalpy of fusion is the amount of energy required to change 1 mole or gram of solid, or 1 mole or gram of solid to liquid at its melting point. Okay. Liquid to solid, it would have a negative heat of fusion. Okay. And then you can do the flat part too for vaporization or condensation. We're going to use this equation. Delta H equals moles times the heat of vaporization. Okay. This is the enthalpy. Let's see if I can spell enthalpy right. will spell it right that time. That's the right way to spell it, Mr. Harridan. Good job. Vaporization. This is the amount of energy required to change 1 mole of liquid to a gas at its boiling point. Okay. Good to know. But basically you have to figure out if you're using this equation, or that equation, and then you have to figure out if it's endo and exo, and then solve the problem. Let's look to see what this means. Let's go to page 7. Page 7. Okay, for each of the following examples, you must calculate the energy, but you first must decide if a temperature change has occurred, meaning we use delta H equals mCp delta T, or a phase change has occurred. Okay, so calculate the amount of energy needed to vaporize 346 grams of liquid water. Heat of vaporization is 40.79 kilojoules per mole. So here I see that we are vaporizing. Okay, which means that delta H is going to be positive, which is this endo. Since we are doing vaporization here, we are going to use delta H of vaporization equals delta H of vaporization times moles equals delta H. And I think that's the equation we're going to use. Yes, it is. By Jove, it is. Okay. So I know the heat of vaporization is 40.79 kJs per mole. I don't have the moles here, so I have to do a conversion here. Remember, you go back to your classic T chart here, 346 grams of water. This is the molar mass, remember, of water, which is 18.02 per 1 mole. You solve that. I get 19.2 moles. I plug in 19.2 moles here. Moles cancel. Sweesh, sweesh. Leave me with some kJs. And delta H is equal to 783 kilojoules. That is my final answer on that one. Okay, calculate the energy change when 1.44 kilograms of water is cooled. Notice that we are cooling here. That means delta H is going to be negative, because this is exothermic. From 98.6 degrees Celsius to 32.3 degrees Celsius. Cp of water, this gives me a good clue of what equation I'm using. 4.184 joules grams degrees Celsius. So since this is not a phase change, this is a phase here. This one was a phase change. We're going to use the equation delta H equals mCp delta T. Okay. The mass needs to be in grams. So 1.44 kilograms. Kilograms on the bottom, grams on the top. 1 goes right here. 1 times 10 to the negative third goes right there. Swish, swish. And I get 0.001. No, I don't. I should get 1044 grams. That is my mass. Cp is 4.184 joules grams degrees Celsius. Now this is the T final and this is the T initial here. So it's actually 32.3 minus 98.6 is negative 66.3. which makes sense because this is exothermic. Exothermic, do, negative delta H, do. Okay, sig figs here. Let's go with 3. So we'll actually figure out what the answer is. .90 times 10 to the 5th kilojoules. Easily done. I'm hoping that you see the difference in these two problems here. One's a phase change, one's a phase. Two different formulas to use. Okay, sketch out a heating cooling curve for bromine here. Okay, so here is a curve, this is time, this is potential energy. Okay, it says the melting point is -7 and the boiling point is 59. So we're going to go from here to here to here to here to there. There's my cooling curve. Okay. Calculate the energy change for 125 grams of liquid bromine. Okay, so this is liquid bromine here. Okay, and when the temperature is being changed from 55 degrees to -7. So again, we are cooling. So delta H should be negative. Because it's exothermic. Delta H is negative. Okay. So again, we're going to use delta H equals mCp delta T. Okay. Again, I'm going to convert my 125 kilograms to grams. Kilograms on the bottom, grams on the top. 1 times 10 to the -3rd. 125,000 grams. Delta H equals 125,000 grams. What's the CP here? Why did I do that in red? Love the bells. 2.3 joules per gram per degree Celsius. So the grams are going to cancel. And then -7 minus a -55 is -62. And I'm going to get a delta H of -1.78 times 10 to the 6th joules. Okay. That was part 1. Part 2. Determine the energy change when 125 kilograms of liquid bromine is frozen at 7 degrees. Okay, so here we're doing freezing. Freezing is a phase change. Okay, as opposed to this liquid cooling, that's just a phase. Okay, so we're doing freezing here, so delta H should be negative. Because freezing is an exothermic process. Okay. This one's even more annoying than the one before. So we're going to do delta H equals the heat of fusion times the moles. Okay. Now this time I have to get the moles here, so I have to do 12500 grams. And I'm going to divide by 159.81 grams per mole because that's the molar mass. I get 782.17 moles. That's going to go here. And I'm going to multiply that times the heat of fusion. Now this is negative now because we're freezing. So this is 10.57 kJs per mole. And moles cancel, and delta H is equal to some number. Negative 8270 kilojoules. Okay, determine the total energy when 125 kilograms of liquid bromine at negative 55 degrees is changed from a solid. Liquid bromine is changed to a solid. Okay. So basically it's asking you to go from, see, the first part we did from here to here on the graph. That was part 1. Part 2 was from here to here on the graph. Okay. Part 3 that is asking us to combine parts 1 and 2. And part 2. But the problem is, one's in kilojoules and one's in joules, so you have to convert one first. I'm going to convert 8270 kilojoules to joules. kJ's on the bottom, joules on the top. 1 goes here, 1 times 10 to the negative third goes there. So it's negative 8270,000 joules. So now I'm going to combine those two numbers here. Negative 8270,000 kilojoules plus negative 1.78 times 10 to the 6th kilojoules. Let's see what we get for a number. Yeah, I missed a 0 in here. That's why it looks wrong to me. Yeah, I got a final answer of negative 1005000 kilojoules, and I'm not going to worry about sig figs for that number because I can get away with that. Okay. Last problem here. Temperature of a piece of copper, 95.6 pieces of copper, increases from 25 to 48 degrees when the copper absorbs 489 joules of heat. What is the Swift key to copper here? Okay, so here the copper is a solid. So that's a phase. Okay. It is absorbing heat. So delta H is positive here. So this is endothermic. So here we're going to use delta H equals mCp delta T. We're looking for the CP. So what we can do here is put in 849 joules. The mass is in grams, so I can use that 95.4 CP. 48 minus 25 is 23 degrees Celsius. Okay, and this is in grams and this is in joules. So first thing I'm going to do here is multiply 95.4 times 23. So this is 849 equals 2194.2 CP. We're going to divide by 849. No, we're not. I lied again. 2194.2. 2194.2 CP is equal to 0.387. And I'm not on the screen. Awesome. Okay, the units. Okay. None of the units canceled here, so this is joules, grams, degrees Celsius. There you go. You guys are champions. Legend is out.